guys, Bauer. Let me do a full screen here. Hey, this is, I think I'm recording for week 3 right now. It's, ooh, my green screen isn't big enough. It's like Sunday of Labor Day weekend, and I need to record like 6 videos today. So you may see a different outfit, you may not. I may have 6 videos in a pink shirt. So I hope everybody's doing okay. I hope this is working out. I hope by week 3 we're getting the hang of this together. So here's the video. All right, guys, today's lesson is about starting to analyze graphs. We have about, 3 or 4 lessons on this. So this one is pretty basic. The first part here anyway is just about, come on. Is about looking for zeros and things. It says by looking at a graph of a function, you can determine the domain and range. Remember, domain is x values, and you read those from the left going to the right. Let me see if I can erase that end. Okay. And the range is y values, and you read those from the bottom going to the top. And you can determine also estimate the x and y intercepts. So this is just where it crosses the x-axis. So it might have, spots here, here. Might be doing something like that. And y-intercepts then would be where it crosses the y-axis. So if it's doing something like this, the y-intercept would be this spot down here. All right, the x-intercepts of a graph are also called the zeros, and that's what our calculator function is. It's the zeros. And that's what you get when you set the y equal to 0. It also down here says they're called the roots, okay? To find the zeros of a function, set the function equal to 0. All right. So one more time, just to fill in the notes, the intercepts are points where the graph intersects the x or y axis. And the x-intercepts occurs when y equals 0 or the function itself is equal to 0. And the y-intercept occurs when x equals 0. In other words, when you plug an x value of 0 in. A function can have 0 or more x-intercepts. So it could have 2, 3, 4, could have multiple x-intercepts, but if it's a function, it can only cross the y-axis once. Kind of the vertical line test. All right. So this is our reminder that x is domain value, domain is x values read left to right, and range is y values read bottom to top. By the way, it's kind of stormy here, so if you hear clunking around, it's probably just thunder. All right. So they've graphed this polynomial, and hopefully they graphed it correctly. I'm assuming they did, because sometimes they're wrong on these worksheets, but I'm not going to redo it. Since the graph continues to go widen to the left and to the right, the domain is just all real numbers. The graph does not go above a y value of 5.0625. So from bottom to top, the range, okay, would be negative infinity up to this y value right here, which is written like this. And remember, unless there's an open dot, we assume it's hitting that value. All right, so we have the square bracket. The y-intercept is the point where it crosses the y-axis. Here it looks like 1, 2, 3, 4.5, right up here. But we can determine that by putting in an x equals 0, which they did down here, and they came out with 4.5 for the y-intercept. So we could write that as 0, 4.5, or we can just list it All right, and then to figure out where it crosses the x-axis, it looks like -3 and like 1.5. But to find those accurately, we have to actually set the function equal to 0. So if we said 0 equals -x² minus 1.5x plus 4.5, then we took out a negative, we'd have x² plus 1.5x minus 4.5. And we don't usually factor with decimals, but this 4.5 is 3 times 1.5. I would not ask you to factor this without whole numbers, but it factors x plus 3 and x minus 1.5, because that would give us a negative 4.5 back here, and 3x minus 1.5x in the middle would give us this 1.5x. Now, I hope you're remembering, but this value can never equal 0 here. It's just a constant. It actually reflected the graph upside down. So that is not one of the zeros, okay? I probably shouldn't have scribbled that out. I don't know. Anyway, -3 and positive 1.5 would make the function equal to 0. If we put a -1 in, it would not. If you put a -1 in back here, it would not make it equal to 0. So there are two x-intercepts at -3, 0, and at 1.5, 0, or you could just write them as a list like they did. All right. So we are to look at this graph and estimate the domain, range, x and y intercepts, and then find the intercepts algebraically. If we look at this graph, domain is going left to right, and it has an arrow on both ends pointing further to the left and further to the right. So we're going to say -infinity to infinity for the domain. The range is bottom to top, and it does seem to be going down and up. So it is also going to cover all y values, so -infinity to infinity. The x-intercept is when y is equal to 0, and that appears to be 2 right here. If we put the function equal to 0, 4 cubed roots of x minus 1, ooh, that's a bad cube root, sorry, minus 4. To solve this, we need to isolate the radical, so we'd add 4 over here, and we'd have 4 equals 4 cubed roots of x minus 1. Then this is a multiply, so we need to divide by that 4, and we'd get 1 equals the cubed root of x minus 1. Now, it just so happens that when we cube both sides here, the cubed root of x minus 1 becomes just x minus 1. Cubed root and cubed cancel each other out, but 1 times 1 times 1 is still just 1. So if we add 1 over here, algebraically, we do get x equals 2 as the only x-intercept, or we could write that as 2, 0. All right, and then finally that just leaves the y-intercept. And the y-intercept is looking like, now be careful, they're counting by -2's here, -2, -4, -6, -8. Looks like the y-intercept is -8. And you get that, remember, when you put in x equals 0 to the function. So f of x would equal 4 cube roots of 0 minus 1 minus 4. Now, some of you are going to argue with me, but you actually can take a cube root of a negative number, because -1 times -1 times -1 is indeed -1. Therefore, the cubed root of -1 would just be -1. All right, let me erase that so the notes aren't confusing later. But the cubed root of -1 is just -1, and then we have 4 times that, minus 4. And 4 times -1. Let's see if I can slide this up. 4 times -1 would be -4 minus 4 would be -8. So when we plugged in a 0, we got out a -8. So we proved that algebraically. All right. Moving on to this example, this is an absolute value function. It says 2 times the absolute value of x minus 3 plus 1. Not graphed super accurately, I found out, especially over here, but we're not going to worry about it. Use the graph to evaluate the function of, okay, f of -2.5 means when x equals -2.5, what y do we get? So f of -2.5 is over here, and it wants to know what y we get. And it looks to me like 11 or 12. And so I'm going to plug it in here to see if I was having you evaluate on a quiz, I would make that come out nice, or I would give you a multiple choice, or I would take either answer if you were just estimating. But algebraically, we do what's in here first. -2.5 minus 3 is -5.5. The absolute value will make that positive. Two times 5.5 is 11, plus 1 is 12. So it is indeed 12, which it looked like on the graph, but I wasn't sure. And f of 1 is when x equals 1. Ooh, that's hard to tell. It looks like we're going to get a 5 maybe. Looks like it's right in between there. So we're going to put a 1 in. 2 times 1 minus 3 plus 1 would be 2 times the absolute value of -2. This will become 2 times 2 because the absolute value makes it positive. So then you get 4 plus 1 is 5. So it does look like it's right in between there. Right? So we estimated from the graph, and we were putting in x and figuring out y at that spot. And then we did it algebraically. Quick questions on domain and range. Just to review again, domain is left to right, and coming from the left, all values are involved until we get here, and then the x value that it stops at is 4, so we say -infinity until 4, square bracket for the domain. The range is bottom to top. This arrow is going down, so from bottom to top, okay? All values going down are good, and it stops here. Now, what students get stuck on sometimes is they will give me the x value where that happens. But remember, range is y value, and the y is counting by ones, right? 1, 2, 3, 4. This graph paper can be confusing, but the y is counting by ones, so we have from -infinity up to 3 is the highest y value. I did not spell that right. Remember. Range uses y values. Gone over that repeatedly, but it's still something students struggle with. All right, on this one, this is really weird. There are x values, again for domain. There are x values, arrow going all the way this way, but then it goes up, and there are no x values here. There's what we're going to call a vertical asymptote, and then the x values pick up again, going this way forever. So we have to admit that there was a value in here where there weren't any. Now, it's a little hard to tell, but this graph actually gets closer and closer. If you think about that, if you put in tiny little numbers here, -2 divided by -0.5 would be 4, but -2 divided by -0.0001 would be like 5,000. Okay, it does, you can get closer and closer. The values you can put in can be anything except 0. Does everybody see that? You cannot divide by 0, so it is all real numbers up to 0, but not including 0. That's why we use the parenthesis. And then on this side, it starts again right to the right of 0 and continues on. Now, you have to say up to 0, but not including 0. That's why we state on the left it goes up to 0, right up to it, but not including. And then on the right it does the same. Now, actually, domain is the same, or range, I'm sorry, is the same, because when we come from the bottom, all the values are good until we get here, and then there's no values here, and then it starts here and goes up again. So again, the range is everything except 0. And I know this is hard for students to understand sometimes, but when you say together with or union of, the reason it doesn't include 0 is because neither of these has a square bracket. So this means it's up to negative 0.00000001 and starting again at positive 0.00000 whatever, okay? Just on the other side of 0. All right, that was the first half. The second half of the lesson is on symmetry here. And this is where I really want you to pay close attention because I worry that this is a concept that can be a little bit tricky. All right, so symmetry of graphs is a concept you learned about in geometry or even before. A graph is a relation that is symmetric to the x-axis or the y-axis. A graph that is symmetric, has line symmetry. So you can fold this graph right along the x-axis and it would match up with itself. Okay, so this is line symmetry. This one you could fold along the y-axis and this would fold onto itself. So it has line symmetry over the y-axis. So the x-axis and y-axis are common lines of symmetry. The other kind of symmetry we learned about in geometry was what's called point symmetry. And that's when you have symmetry around a point. It's a rotational symmetry of 180 degrees. It means that you can take a picture of this graph, rotate it 180 degrees, and it will look exactly the same as it started with. Okay? So that is what rotational symmetry or symmetry about the origin is, and it's called point symmetry. And the origin is the point we're going to worry about. Other things can have point symmetry, but we're only going to worry about ones that turn exactly around the origin. Okay? There are tests for symmetry, and these can be a little bit confusing. I think I'm gonna just, well, let me run through this. If a graph looked like this, it has x-axis symmetry, which means a point, for example, like over to and up to, right here, would also be matched by a point that went over to and down to. So when it has x-axis symmetry, the opposite y value is also on the graph. So if it's symmetric to the x, we can replace the point xy with the point x opposite of y, and it will also be on the graph. Algebraically, when we put that in, we replace y with the opposite of y, and everything will cancel out so that we get an equivalent equation. When it has y-axis symmetry, think about this. This one folds along the y. So if this had been the point, we'll say 2, 4. Then we could also go left 2 and up 4, and we'd find a point. It has to match when the x changes on opposite sides of the x, it has to be the same. That's when it has y-axis symmetry. Okay? So what you do to check is replacing x with the opposite of x, will result in an equivalent expression. For example, this graph kind of looks like y equals negative x squared plus 6 or something. If I put a 2 or a negative 2 in here, when I square it, they both become 4. Okay? So I was making up an equation, and it doesn't match what I put over here, but an x squared with no other form of x would be an example of y-axis symmetry. All right, origin symmetry, a little bit harder to think about, but if you went, say, over 1 and up 5 up here, we'll say. Looks more over more than 1, but anyway, I made up a number. Then also you could go left 1 and down 5, and you would find a point on the graph because it has to spin around 180 degrees. The same would be true if our original graph had been in quadrant 2. When we spun it 180, it would be down here in quadrant 4. Okay? So the test is you replace x with its opposite and y with its opposite, and then when you simplify, it should get back to the original equation. All right, we're going to fill that in here. For if it has x-axis symmetry, let's draw a super easy one. X-axis symmetry would look like this. Whoa. Okay, I didn't draw that well. Let's just do a V. That might be easier for Hofbauer to draw. Does that look like a V? Not really. Okay, so that would have x-axis symmetry, goes up and down the same amount. So every point x, y on the graph, the point with the same x but the opposite y is also on the graph. Make sense? Here and here. So replacing y with the opposite of y has to result in an equivalent equation. Please notice this is not a function when it has x-axis symmetry. All right, y-axis symmetry, that same v might, or something, we could do a parabola, we could do, we'd make something complicated here. How about a McDonald's arch? Okay, I didn't draw mine very accurately, but if this was perfectly symmetric, okay, then every time you went to the right or left the same amount, it would have to match up. So y-axis symmetry, for every value like 2, -2, there has to be a -2, -2. So the x changes sign to indicate a left or right. So every time you replace an x with an opposite of x, it has to result in an equivalent equation. And then finally, origin symmetry might look like this. I'll draw it in these quadrants this time. Okay, so for every xy, when you change the sign on both, so if we went -2, +4, we would go +2, -4. So you would change the sign on both, and that would still be symmetric, so or still be equivalent. So replacing x with the opposite of x and y with the opposite of y results in an equivalent equation. All right, pause if I went too fast there, but this is what you need to memorize, okay? Functions that are symmetric with respect to the y-axis are called even functions. Even functions. A function is even if it is symmetric with respect to the y-axis. So the algebraic check for y-axis symmetry is x, y is equivalent to the opposite of x, y. Okay? I don't think that's how they wrote that. They wrote f of x is equivalent to, and you put the negative in for the x, so it's f of -x. Okay, but it means you replace x with -x. All right, a function is odd if it is symmetric with respect to the origin. Now, the reason we don't have x-axis listed here is because x-axis symmetry does not make a function, okay? Not a function at all. And again, the algebraic check for this is you have to change both the x and the y. So you could trade out x for the opposite of x and y for the opposite of y, and it should be equivalent. Or as they say, the opposite of the original function is the same as when you put in the opposite x value. This would mean negative y equals putting in a negative x, okay? That's kind of confusing, so I'm going to erase that. All right, so normally what we need to do is just graph these. Sometimes it's hard to tell by the graph. I'm going to give you a tiny little hint in a minute when we look at the functions. It most often has to do with the exponent values, all right? Y-axis symmetry can be things like this or things like this. Oh, that's horrible. I can't sketch. And what happens is these are things that have even exponent powers. Like this might be y equals x squared. This one might be y equals x plus 2 squared times x minus 2 squared, where all the exponents are squared. All right, I'm going to try and write it. Odd functions is when all of the exponents turn out to be odd. Y equals an x cubed looks like this. Okay, so that's my little hint. All right, so we are to look at this graph, y equals x cubed plus 2x. Now notice the exponent here was 3 and the exponent here was 1. Those are both odd numbers, so I'm thinking it's an odd function. That is not necessarily the only thing indicating that, but if you graph it, okay, on the calculator they graphed using a regular Zoom 6 window, and they typed this in the y equals. They got this graph, and so therefore it does look the same if we turn it 180 degrees. So it appears to have symmetric, let's see, the function is symmetric to the origin. If you confirm origin means you have to change both signs. So back up here, I'm going to make it say the opposite of this equals the opposite of, and I'm putting an x in here and an x in here, an opposite of. Now we got to think about that for a minute. Negative 1 to the third is still negative 1. So I still get a negative 1x cubed when I get rid of the cube here. And back here, 2 times negative x would be a negative 2x, or minus 2x. Now the opposite of this would become a 1x cubed. But remember, we started out, we had to put in an opposite over here. So if we divide everything by negative 1, we get y equals negative 1x cubed and a plus 2x, which is what we started with way up here. So therefore, we're changing the signs on both, eventually got us back to what we started with. Okay, that really goes on this blank right here, I guess. So the function is origin symmetry, means the function is called odd. All right, symmetry to the origin is called an odd function. So we are to look at these graphs and determine whether they are even, have even, it doesn't even use those words. It says, determine if the graph is symmetric to the x or y or origin, and then it says we can talk about even, odd, neither. Now, if you look, this has a degree 4 and degree 2 up here. So those are both even, and it does in fact appear to have symmetry around the y-axis. So we're going to mark y-axis, and y-axis symmetry would make it an even function. This is a tricky one. I cannot fold it here because then I would get something here and something here, okay? I cannot fold it up and down or across the x-axis, up and down over the x-axis or across the y-axis, but I can turn this 180 degrees and it'll look exactly the same. So that's origin symmetry. And origin symmetry, remember, means that it is an odd function. Okay, origin, odd function. Notice this was not even solved for y. Okay, so we couldn't tell just by looking at that equation. This equation is also not solved for y, a little bit trickier. It does have two even exponent powers, but we got to think about this. Can we fold it across there and it will match up? Yes, we can. So it does have y-axis symmetry. Could we also fold it across the x and it would match up? The answer is yes. And remember, x-axis symmetry means it's not a function. So therefore, even though we can spin it 180 and it has origin symmetry, it's not a function, so we can't call it any of these. I guess you could say neither because it's not a function. Okay, so can I have symmetry and still not be even or odd? This one, if this was going through the origin, it would have would be odd. I think we could spin it 180, but it's not going through the origin. If I fold it across the x, this piece is going to come down here. This piece is going to go up here. It's not going to match up. If I fold it across the y, this point that was over here at 0, 1 is now going to be over here. Okay. If I fold it across the y, you got to think about what that would look like. This piece would fold, it would go this way, and this piece down here would go this way, but it wouldn't match up exactly where it was. So this has none. This one, if I flip it across the x, would be up here, so that isn't working. If I flip it across the y, then this would go here, and this would go here, so it does have y-axis symmetry. If I turn it 180, it will again be up here, so it does not have origin symmetry. And it is a function, and y-axis symmetry means even. Now, do you remember I said you can't just look at the exponents? All right, there is no exponent in here, but the absolute value makes everything positive. You have to look at the graph. It is an even function. All right. Determine algebraically and test if these are even, odd, or neither. I'm going to guess by looking at this that there's a 3 and a 1 here, so that this might be an odd function. What we need to do is graph it, but we're also going to have to test it algebraically. If I go to y equals and I type in x to the third minus x, and I do a zoom 6, I get this shape. I think this might be one we already tried today, or was it the opposite? This shape, okay, does indeed appear to have origin symmetry, so I'm thinking it's odd. The odd or origin symmetry test, I could go through all of them, it's kind of painful, but I think it's origin symmetry. So what I'm going to do, the test for that is change both. This f of x becomes the opposite, and all of these become the opposite. And then we see what happens. Well, when you cube a -1, it's still a -1. And the opposite back here becomes plus x, and we still have a negative over here. Then if we divide everything through by -1, it becomes y equals, this would become positive x cubed, and this would become negative x. So it does go back to what we started with. So it has origin symmetry. I don't really want to prove that it doesn't have either of the other two. Are we good with that? This, if you graph it, I believe will look like this. I'm thinking it has y-axis symmetry, which means you change out the x. So you have y equals negative, change out the x. Well, what happens when I take a negative x and I square it? Negative 1 times negative 1 is positive 1. So this becomes a positive 1x squared. And then the one out front makes it a negative. And isn't that what we started with? Okay, so replacing x with the opposite of x had no effect. That's because if I go over this way to the right or to the left, I have points in the same, with the same y value. So therefore it has y-axis symmetry, which is, it says even, odd, or neither. Y-axis is even. And let me talk a little bit about the exponents. This had an exponent of 2, and this had 0 x's on it. These are both even exponent powers, okay? X to the 0 is just 1, and 0 is an even number, all right? I know it's hard to think about that, but 0 is even, because if I list out -2, 0, +2, 4, those are all even numbers, counting by 2's. All right. This one, if I look at the exponents, I have odd, even, odd. I'm thinking this might be none, which means we probably need to test them all to show that it's none. To change x for the opposite of x, we would end up with a -1x cubed. This would be a -x squared in here, but then this one would make it a positive. And back here, negative times a negative would be a positive. Okay, so we changed out x, which checks for y-axis symmetry. And it is not equivalent to what we started with. So it does not have y-axis symmetry. We could graph it and look. It is not going to have, it's not x-axis symmetric because that isn't a function. It's not one of our choices anyway. We just need to determine, so it's not even here. We need to determine if it's odd. And the test for odd is you change both. So we have -y equals -x cubed minus -x squared. Inside here, -2 times -x. We have -y equals, when you cube -1, you still have -1. You square this, it would become +x squared, but then this one out here would make it a negative. Our negative times a negative is a positive. Now we have to divide through by -1 everywhere to get the y. Okay, multiply or divide everything by -1, and we get y equals a +x cubed, a +x squared, and a -2x. Is that equal to what we started with? Nope, because of that sign right here. So it's not odd either. So this one turned out to be neither. And that leaves this guy over here. If you graph this, and I'll even show you, y equals, what is it again? The square root, second x squared. I don't know how I got that squared there. I must hit it twice, but that's okay. X squared. Minus 4, and make sure it's all under the radical. That's what I was supposed to have. Yep, okay. Graph it. This is what we get. It's a very misleading graph, honestly, because it does go all the way down and touch right here. I think maybe if we did a zoom decimal, we would be able to see that. Really doesn't matter. The bottom line is it looks like it's flipping across the y-axis, so it appears to have y-axis symmetry. The test for y-axis is replace x with its opposite. So we have y equals the square root of negative x squared minus 4. This squared becomes a positive 1x squared. It is indeed what we started with. So the y-axis symmetry test works. So it is an even function. All right, so that's the basics. You need to do some book work. Again, on the resources tab in our Google Classroom, there is information about how to get into the book, but I believe this is the second book assignment, so hopefully you figured that out by now. And do these questions. It looks like a bunch of them ask for just domain and range, or is it an even odd function? Okay, very few do you have to do a lot of extra work on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 questions. You got this, guys.